we're going to finish our discussion. We introduced the idea of changing variables generally for multiple integrals, and today we're going to talk about developing what's called the Jacobian, which will be the correction factor for these matrices after we've made our change of coordinates. All right, so we're going to start more general form of what we had looked at before. We're going to say we're in the UV plane and we have some region S. Okay? If you think about the example we did in the prior lesson, the rectangle had a vertex of 0, 0. This one doesn't. It's just a little bit more general. And then over here is the XY plane. And what we know is that there's a transformation. It's going to take the region S into a new region in the new plane that I'm going to refer to as R. And you can't be sure that this new region is going to look the same. So maybe it looks something like this. It's some kind of arced rectangle of sorts. This is the region R. Okay. And the transformation T is the thing that takes us from one to the other. Now, a transformation like this we can write as a vector valued function. We can say R of UV is equal to G of UV times I plus H of UV times J. To refer back to the example we already looked at, the example of the vector value function we had dealt with before was that x was equal to, well, we'll say it this way, G of UV was equal to U squared minus V squared. But you'll notice that's the coefficient on I, which always gives us the x component of our vector. Okay? We're being specific, we're saying that this is a position vector, meaning that this vector valued function is going to be vectors that point to points on the xy plane whose coordinates are equal to the coordinates of these vectors. So, fancy way, but saying that, sorry about that, but sometimes you just got to go through it. So y is equal to h of u comma v, or 2uv. Now, I'm not going to work, we'll eventually work out the Jacobian for this specific example, but we need to do a little bit of theory first. Okay? All right, so that was the example we had dealt with, a vector value function, but we have this transformation. So I'm just going to label a few things, and then we'll start to develop some ideas. All right, so I'm going to call this lower left corner of the region S in the UV plane. I'm going to call that U0, V0. Okay? And I want you to imagine that this region S in the UV plane is a really small rectangle. And that's sort of nice to have it be a rectangle, because then we know our limits of integration are going to be nice things like U is going to vary from U0 over here to out here, which is I'm going to call this U0 plus delta U. Okay? Delta U. Now, why would that be a good name for delta U? Well, if you think about a small change in this direction, we move horizontally in this plane. A good name for that would be delta U. And then in the same sense, same spirit, this is delta, bear with me for a second there, sorry. That's delta V. Okay, so now we know maybe this coordinate out here, this is V0, and then this is V0 plus delta V. It's not really a coordinate, it's just that's the V values and the U values. All right, so there you are. We've described our rectangle. And what we know now is if we look over at the region R, for example, this side here, we can corresponds with that side. That's how that side got transformed. So let's think about the equation of this side of the rectangle in the UV plane. That would be U is equal to U0. U0 is a constant, and U is never varying on that line. So over here what you have is the image of that is UR of U0 comma V. In other words, we're plugging U0 into this vector valued function down here, and we're getting what X and Y look like. Okay? And then in the same sense, if we think about this side of the rectangle down here, we'll say it gets mapped over to this position, and then this side would have the following vector valued function. It would be R of U comma V0. All right. And then while we're at it, for consistency's sake, we'll say that this point here has coordinates x0, y0. Oh, hold on a second there. X0 comma y0. And it's the image of u0, v0. So that's what happened when we applied t to u0, v0. Okay. So now that we've done that, we can start to do a little bit more development. Let's think about our goal here. Clearly, the area of this thing, the dA for S, is just delta v delta u. That's what it is. Okay? The question is, what's the dA over here? What's that thing going to equal? Okay? All right, so that's really what we're trying to figure out, and that's what we're going to go with. Or if we knew this dA, say we knew dA in the xy plane, which is always easier. Suppose we knew dA was dx dy. Question is, hey, what corresponding dA would we have over here? Isn't there a correction factor that goes in here somewhere? And the question is, what is that correction factor? Okay, so I think we stated the question and where we're heading. Let's redraw this picture here. So here's the xy plane. We're in the xy plane again. Okay, and I'm going to draw that region R again. Here it is. A little exaggerated version of it. Okay, and we knew that this green thing here, that was R of u0v. And then this black thing along the bottom, to be consistent, that was R of u comma v0. All right. So here's what we're going to do. What we're going to do is just recall a couple of things we know about vector valued functions and their derivatives. So if we were to consider this quantity, R sub v of u0v, that's the partial derivative of the vector valued function in the v direction. Okay, and what would that end up giving us? That would actually give us this vector here, this tangent vector. Okay, and that's what that is. Okay, and then similar reasoning, that vector has a good name. We'll call that R sub u of u comma v0. All right, so there we are. All right, I'd like to get them involved somehow. We're going to shortly. We're just going to do one more thing. All right, so what I'm going to do now is I guess I'll use the color blue here. There's a good name. I'll use black instead. There's a good name for this vector. We can actually name that vector. We can find that vector. That vector, I'm going to call that vector A for the time being. And what we can say is that vector A is going to be this point up here, whatever that point is, minus this point down here, this point. So that's what we have to do. But we actually know the coordinates at that point. The coordinates at that point are R of u0 comma v0. It's a transformation applied to this corner point here, and it lands over here at x0, y0, which I could have written that here. I could have called this thing x0, y0, but I'm going to call it R of u0, v0. I want to keep it in terms of the vector valued function that represents the transformation. And then this point over here is R of u0, comma, v0 plus delta v. That's the image of the upper left-hand corner. It's that point. And the coordinates at that point are u0, comma, v0 plus delta v. Okay, great. So in this picture then, we can actually get the vector A. The vector A is going to be R of u0, comma, v0 plus delta v minus R of u0, v0. That's what the vector A is. All right, we're going to do a similar story down here, so I don't lose track. I'll use green here again now. I'm going to call that vector B. And vector B we can find using the same reasoning. Now we know we're going to be subtracting R of u0, v0 because it has the same, I will say that, the same tail of the vector, all right, the same starting point. And then we got to get this coordinate. Well, that coordinate would be the image of this lower right-hand corner, which we know has coordinates u0 plus delta u, comma, v0. So this point is going to be R of u0 plus delta u, comma, v0. And then that's what's going to go here. So now we have R of u0 plus delta u, comma, v0. All right, so now we have the vectors A and B. All right, so what can we say about this? Well, we're going to make some approximations now. Here's what we can say. What we can say is that this first vector, let's be careful here, this vector here, which is the vector A in the picture, would be well estimated by this partial derivative multiplied by a small change in v. So what I'm going to say is the partial derivative in the v direction at that particular point multiplied by a small change in v is going to give you a good approximation for this vector A that we drew in the picture. Okay, so you have to sort of believe that. And then similar reasoning will tell you that this directional derivative, or I should say, no, this part is a directional derivative, this partial derivative with respect to u at u0, v0, multiplied by delta u, is a good estimate for this expression, u0 plus delta u, comma, v0, minus r of u0, v0. So that's what we have. Okay, so I mentioned this because we actually know what we were looking for. We're getting very close to what we're looking for. Let's keep in mind our goal here. Our goal is to figure out dv. In other words, like, so if we know dv is, we want to get that correction factor. And what we remember is something from cross products of vectors. We know that if we have the vector b here and the vector a, and if we were to find the norm of a cross b, then that gives you the area of the parallelogram that's spanned by the vectors. Okay? So it's a really handy thing to know, and that's actually what we're going to utilize here. All right, so the norm of the cross product of two vectors is the area of the parallelogram spanned by them. So what does that mean? It means that if we wanted, we could find the cross product between that vector and that vector, and if we did that, we would get a vector. We take the norm of it, that would be the area of the parallelogram spanned by the vector. But I've said it's also very well approximated by these two things, especially when delta v and delta u get small. Okay? So actually, that's what we're going to do. What we're going to do is we're actually going to grab this side, and we're going to take the cross product of these things. I'm just going to write it this way. R sub u delta u times delta u cross R sub v times delta v. You notice I'm not writing that I'm subbing in these points. We're just going to assume that. I'm saving myself some space on the page here. Okay, but we know some properties of cross products. You need to go back and look at things. But basically, delta u is like a scalar. Delta v is like a scalar. So we can factor those out, and we get this. Ru cross Rv times delta u delta v. Okay? And that really comes from, we talked about what that is. All right, but now we actually know how to find a cross product. Okay? So let's remember what Ru is. Ru is the directional derivative in u direction of that transformation. So we can write that a couple ways. Let's take a minute just to remember. R of uv is equal to g of uv I plus h of uvj. So what I could say is that R sub u of this thing is going to be partial g partial u and the I times I, and partial h partial u times j. Okay. Now I'm going to do something else for you. Traditionally, we're going to be calling this x and this y. In other words, this part of the transformation times I gives us what the x coordinate is going to be after we do our transformation. This is going to be the y coordinate is going to be. So I'm going to write this a third way. Not a third way, a second way. I'm going to write it like this. Partial x partial ui plus partial y partial uj. And I'm calling that r sub u. All right. And then in the same, using in the same spirit, if you work things out, this is going to end up being partial x partial v I plus partial y partial v j. All right, and once you have that now, we can write the cross product. So remember, cross products we do with this special determinant. So RU cross RV is going to be IJK. And then you have in here RU first. So partial x, partial u, partial y, partial u, and 0. Of course, there's no k component of that vector. And then this is going to be partial y, partial u, partial y, partial v. Okay. And then this was v, sorry, and 0. Okay. So then we're actually ready to go, because now we know how to find that determinant. Now, determinants are done the following way. You take I and you multiply it by its minor. Its minor would be the matrix that's left over when you cross out the column and row that I is in. You'd get this. But this determinant is 0, because you're going to have 0 minus 0. So that doesn't count for anything. And then you're going to do the same thing here. You cross out j, row and column. The thing you're left with, you have du dx times 0, du dy, that's going to cross out to be 0. So actually, the only thing that's left here is going to be the following. Partial x, partial u, partial x, partial v. And then here you're going to have partial y, partial u, partial y, partial v, k. And that's what you end up with. Well, the norm of that is just going to be, since k has unit length, it's just going to be this. So this thing is the norm of that, which is the area of the parallelogram, and hence your correction factor. So that correction factor is referred to as the Jacobian. Okay? Alrighty then. So that's it. That's where the Jacobian comes from, basically. I guess I could say thanks for watching there. I appreciate it. And that's it. The next video will actually do an example.